This is Unit 4, Lesson 10, Part 1. So we are nearing the end of this very long unit. We're looking at projectile motion, which is a really important application that we can do with these quadratic equations that we've been working with. So we're going to start with number 1. It says a soccer ball is kicked from the ground with an initial upward velocity of 90 feet per second. So this equation right here gives the height of the ball after t seconds. So if you visualize the way a soccer ball would be kicked and go up and go down, it forms this upside down parabola. And parabolas are quadratic equations, which is why this is a connection to what we've been doing. So it gives us the equation. You can see this is a quadratic. So part A asks, how many seconds will it take for the ball to reach its maximum height? So maximum height of a parabola is like the vertex. So remember doing the vertex, we've got that formula. So seconds means that we are solving for t. So how many seconds means we want to solve for t will it take for the ball to reach its maximum height? Note they don't ask for the maximum height, just the time that it takes to get there. So we are going to start with our vertex formula. So if you remember this, I'm writing t instead of x, but it's negative b over 2a. We've been working with that for a while. So negative b is 90, so this is negative 90 over 2 times a, so 2 times negative 16. So this ends up being, the negatives cancel. We have 90 over 32, and I would say it makes the most sense to just get that as a decimal. So 90 over 32 is 2.8125. So after that many seconds, that's when the ball is going to be at its maximum height. So then part B asks, what is the maximum height of the ball? So at that point, we want to take this time and plug it into this equation. So in function notation, we're finding the height at 2.8125, and that means this number is going to get plugged into this equation in both the spots where there's a t. So negative 16 times 2.8125 squared plus 90 times 2.8125. I guess I should probably write the answers up here, right? This is seconds. Now this guy right here, feel free to just plug that into a calculator because it'll do the order of operations for you. So I'm typing in negative 16 parentheses 2.8125 parentheses squared and then plus 90 times 2.8125. And what that gives me is 126.5625. So I'll write that in my answers here. And all these problems are going to have units, so you want to make sure that you're including your units. So read through here, and this is feet. So that is the maximum height of the ball. And finally, part C, give the domain and range of the function. So we want to include, so domain is normally all the x's, but now it's all the t's, and y is, range is normally all the y's, but here it's all the h's. So domain is all the possible values of t, the range is all the possible values of h, because those variables have now replaced our x and our y. So the domain. For the domain, we want to know when it's going to be on the ground, like from when it starts on the ground to when it ends on the ground. That's what we need to know, because once it hits the ground again, we kind of stop the clock on the time, right? So we want to see when this equation is equal to 0, because that's when the height is 0. So that's when our problem kind of begins and ends in terms of the time. So this is actually factorable. Anything that has just 2 pieces right here, you're able to factor it by taking out a GCF. So these we can take out a 2, might as well take out a negative 2, and a t. And then in parentheses, divide this by negative 2t, and I get 8t. Divide this by negative 2t, and I get negative 45. And we set this equal to 0. So set each piece equal to 0. When I set this equal to 0, I can divide by the negative 2, and that just leaves me with 0. And that makes sense. At t equals 0, the ball would be on the ground, because we haven't kicked it yet. And then this is when it would land back down. So t equals, we would add the 45 to both sides and divide by 8. Let's get that as a decimal. That is 5.625. Okay, so for our domain, let's write all the values of the time. So the domain is in between 0 and 5.625. So this is the domain, the values of time when the ball was kicked, when the ball landed back on the ground. And then for the height, we want the lowest and highest height. So the ball started on the ground, should be 0. And then we already talked about its maximum height right here. So the height is always in between these two values. All right, so that's the first one. That kind of covered a lot of the different applications that we'll be using. I want to look at the very next one as well, number 2. Number 2 says an apple is launched directly upward at 64 feet per second from a platform 80 feet high. One important thing, we don't actually do anything with these numbers. The initial velocity is always the value of b, and then the initial height is always the value of c. So like you don't have to do anything with those numbers. It's just telling you what ends up appearing in the equation. We actually had the same thing here. Initial velocity of 90, that was just the value of b. So you don't do anything with those numbers. It's just already in the equation. Negative 16 is acceleration due to gravity. If any of you have taken or are currently taking physics, that's what that negative 16 is. So question here just asks, what's the height after 3 seconds? So in function notation, we are looking for the height if you plug in 3, because 3 seconds, that's a value of time. So like when they tell you this, they're telling you that t equals 3. And if we know that t equals 3, you just want to plug it in to this equation everywhere that there's a t. So negative 16 times 3 squared plus 64 times 3, and then plus 80. So this, again, feel free to just plug it right into your calculator. Let it do the order of operations for you. So I'm plugging in negative 16 times 3 squared plus 64 times 3, and then plus 80. So this gives us 128 is the actual value that we get. So make sure when you write your final answer, it includes units. So the units would be feet, 128 feet. So that's one, just kind of a simpler one where all they really wanted you to do is plug a number in. The next one I want to look at is number 4. Number 4 says a penny is dropped off the Empire State Building, not supposed to do that by the way, which is 1,250 feet tall. So this is like your initial height that appears here in the equation. If the penny's pathway can be modeled by this equation, how long would it take for the penny to strike a 6-foot, that sounds violent, strike a 6-foot tall person? So notice here there's no t, and that's because t is the initial velocity. If something is just dropped, it has no initial velocity, which means it's 0, and that's why that term isn't there. So how long would it take for the penny to strike a 6-foot tall person? This is a value of h that they're giving us. They're telling us that h is 6, and when they say how long would it take, that means that they're asking us to solve for t. Okay, so they're giving us a height, asking us to solve for t. So we're going to replace the height with 6. So we're going to say 6 equals negative 16t squared plus 1250, and then we can solve for t, which is what they're asking us for. So different methods that we've used. There is no term for t, so that means we can use the square root method. If there's no middle term, we can solve by taking the square roots. So what we do is we get the squared term by itself. So I will subtract 1250 from both sides. So 6 minus 1250, that is negative 1244, is equal to negative 16t squared. Still working on isolating that t squared, so we divide both sides by this negative 16. We get 77.75 is equal to t squared. So now that t squared is isolated, what we do next is take the square root of both sides. So take the square root of this, take the square root of this, and you're just going to want to use your calculator. It's going to be a decimal value. So square root of 77.75. So we get the t by itself, and then remember when you solve equations by taking a square root, you always use a plus or minus. And this would be 8 we'll do 3 decimals, 818. So I just plug that right into the calculator. So for my actual answer, the plus or minus, you always do that when you're solving an equation, but in terms of time, the negative answer wouldn't make sense. Like it wouldn't have happened negative seconds before you dropped the penny. So only the positive one makes sense for our actual problem here. So we are going to say 8.818, and this is given in seconds, I believe. I guess it doesn't specifically say that. Let's just assume that it's seconds. Okay, so we did a few of those on the fronts. I want to do a couple more on the next page. The next one we're going to look at is number 7. Okay, so number 7 here says, Eva is jumping on a trampoline. Her height h can be modeled by this equation. So notice this is always going to be there because that's acceleration due to gravity. That's not changing. This must have been her initial velocity, and then this is her initial height. So this must be how tall the trampoline is. That seems crazy tall, but that's, she must have climbed a ladder, I guess. So we have acceleration due to gravity, initial velocity, initial height. So this is asking, would she reach a height of 14 feet? Okay, so what we want to do is treat this kind of like the problem on the front where we found the maximum height. So we can find her maximum height, and then we just want to see if it's more than 14. So this is kind of going to be a yes or no question. So let's go through and find the maximum height. So we look for the vertex first. So the vertex, remember, is negative b over 2a. So negative 20 over 2 times negative 16. So negative 20 over negative 32, we'll get that as a decimal. So that is 0.625. So that's when she reaches her maximum height. Jumping obviously goes very quickly. So this is when she reaches her maximum height. We want to see what the actual maximum height is. So this is just like we did for part B on number 1. So we're plugging this into the equation, and we're going to see if it's more than 14. So this is just replacing the t. And I'm just going to plug this into my calculator. So negative 16 times 0.625 squared plus 20 times 0.625 plus 6. So this comes out to be 12.25. So that means her maximum height is 12.25. So that's what we figured out. That's the vertex. That's the highest that this parabola will ever go. So if her maximum height is 12.25 and they say, would she reach a height of 14 feet? The only answer we need to give is no. Obviously, you have to have the supporting work shown there, but this is just a yes or no question when it comes down to it. All right, we're going to do one more, the last one, number 9. This one says, an astronaut on the moon throws a baseball upward with an initial velocity of 10 meters per second. So that's where this 10 comes from right here. Letting go of the baseball 2 meters above the ground. That's the initial height. And then this is the equation. So this is on the moon. So we are going to have a different acceleration due to gravity on the moon because gravity is a lot less. That's why it changes the value of a here, and it's never been different before. The same experiment is done on Earth. So this one right here, we've got negative 4.9. The reason this is different is because we're working in meters. All the other ones were working in feet. So acceleration due to gravity, if you're working in feet, is negative 16. If you're working in meters, it's negative 4.9. And that's just because 4.9 meters is the same as 16 feet if you use the conversion. So here's our Earth equation. Here's our astronaut on the moon equation. So this is how much longer would the ball stay in the air on the moon compared to on the Earth. That makes sense. Less gravity, it would stay in the air longer. So we're going to do something similar to what we did with the domain and range for the first problem. We want to know when it hits the ground again. So we're going to set those equations equal to 0 and then see when it actually lands back on the ground at each point. So we are going to take the moon one, the negative 0.8 t squared plus 10t plus 2. We're going to set that equal to 0. And then to compare, we're going to take the Earth one and set that equal to 0, because a height of 0 would mean it's back on the ground. Okay, so we're going to plug that in. So these, I would just jump right into the quadratic formula. It's not worth trying to see if they can factor, and I'm assuming they won't since we have these decimals. So quadratic formula, we've got x equals, except it's going to be t equals because we changed our variable, negative b plus or minus square root of b squared minus 4 times a times c all over 2 times a. So just plug it into the quadratic formula. Let's see what we get here. So we have negative 10 plus or minus square root. I'm going to just plug this whole thing into my calculator. So 10 squared minus 4 times negative 0.8 times 2. So under the square root, I end up with 106.4. All of that over 2 times negative 0.8. So that is negative 1.6. Okay, so let's get our two different answers here. So square root of 106.4. This is 10.315. So just that square root is 10.315. So negative 10 plus 10.315, and then divided by negative 1.6. So when I do the plus, I get negative 0.197. And then I'll do the minus, negative 10 minus 10.315 and divide that by negative 1.6, that gives me 12.697. So in terms of time, we don't want the negative one. So this is how long it took for the ball to go up, to go down, and land back on the surface of the moon. Now we can do the same thing for Earth. So t equals negative b plus or minus the square root of b squared minus 4 times a times c, all of that over 2a. So we're going to compare and see what the actual difference was between those. So plug this in, negative 10 plus or minus, under the square root I have 10 squared minus 4 times negative 4.9 times 2. So under the square root I have 11.798, all of that over negative 9.8 when I multiply these together. Let me get a value for just that square root. That is 3.435. So I'm going to do 10 plus or minus that number over this number. So negative 10 plus that answer divided by negative 9.8. That gives me 0.669. And then let's do the other way. So negative 10 minus that answer, all over negative 9.8. Oh, I think I did something. Let me just see. Something was plugged in weird with that square root. I'm sorry, I need to try this again. 10 squared minus 4 times negative 4.9 times 2. Yes, this should be a different number right here. I'm sorry, we're going to try this again. These numbers weren't looking right. 139.2 is what should be under the square root. My apologies. So square root of that gives us 11.798. I accidentally took the square root early. So that right there, let's try these again. I'm sorry. So negative 10 plus that answer divided by negative 9.8. That gives us a negative 0.184. And then if I do the minus, I get negative 10 minus that answer divided by negative 9.8. And that gives me 2.224. So not this, because I don't want the negative one. So finally, this is how long it took to land on the moon. This is how long it took to land on Earth. How much longer would the ball stay in the air on the moon compared to on Earth? So how much longer means we want the difference between these two. So I'm going to type in 12.697 minus 2.224. And what that gives me is 10.473 seconds.